Let's talk about confidence intervals and probability estimates. And we're going to do this in the context of the normal distribution. This is really the distribution we're going to focus on. And it's just a function. It's just a function y equals some function of x. F of x is equal to some function. And you can see here that the function has, really just a single input, and that's the x right here. Now there's a couple of parameters. That's the mu and the sigma, and we'll get to that. But everything else is sort of a fixed number. Pi and e are all fixed numbers. And so for some given x, you plug it into this x, or you plug it into this equation. Given some mu and some sigma, it spits out a y. And that's essentially the height of the curve at that value of x. And we can use this as a probability density function because it has some very important points, very important properties. And the very first one is that the area under the curve always sums to 1, regardless of the value of mu and regardless of the value of sigma. If I integrate this function from negative infinity to positive infinity, there's always an area under the curve equal to 1. And if it's really skinny and really tall, then it's 1. And if it's really flat but really wide, it's still 1. And so the area always sums to 1, which makes it very useful as a PDF. And the other thing that's nice about it is it's very tractable. There's only two parameters. There's mu, which is the midpoint, and then there's the sigma, which tells me both the height and the width. The other really nice thing about this is it actually comes close to representing stuff we observe. A lot of things are pretty close to normal. Now, it may be too simple. It may not describe reality, perfectly, and we'll look at this in the context of estimating essentially left tail events, right? What's the likelihood of something really bad happening? Are we overestimating or are we underestimating, assuming normality? But we'll come back to that later. For now, let's just realize that this is a function. There's a y, or sort of an f of x on the left side, and there's a whole bunch of stuff on the right side, two parameters, a mu and a sigma. I plug in an x and it spits out a y. And that's just like this equation, which is nice and simple. Y equals a plus b x. And for any given a and b, I plug in an x and I get a y. The same way for any given mu and sigma, I plug in an x and I get a y. And so for in this particular case, if I have two parameters, a equals 2 and b equals 0.5, I can draw this curve and it can tell me everything I need to know. Okay, so the interpretation of the normal distribution. So the normal distribution, because it has this very special property, it's always the case that if I'm looking at the mean plus or minus one value of sigma, I'm always going to have roughly 2/3, 68.26% of the area under the curve between these two values. And if I go out to a second standard deviation, I'm going to have 95% of the area under the curve between these two values. And then 3 standard deviations is 99.74%. In this particular case, we have a mean of 10% or an expectation of 10% and a standard deviation of 20%. And so I can say that given that this is normal, the mean minus 1 standard deviation, which is 10 minus 20 brings me to negative 10, and the mean plus 1 standard deviation, 30%, I can be 68.26% confident that any observation will fall between negative 10 and positive 30, plus or minus 1 standard deviation. Now I can be much more confident about a wider interval. I don't have to go out an integer number of standard deviations. We'll just do this for now. But I can be 95% confident that any outcome will be between 10 minus 2 times negative 20, so minus 30%, and 10 plus 2 times 20, 50%. So I can be 95% confident of an observation in between minus 30% and plus 50. And then, of course, I can be 99% confident minus 50 and plus 70, the mean plus or minus 3 standard deviations. Okay, so let's, for now, assume that returns are normally distributed. And we know this doesn't really make sense because we can't have a return that's greater than negative 100. And we're going to see later on that this thing isn't really perfectly normal. But for now, we're going to assume that returns are fully described with just 2 parameters. And the other way to think about it is that the returns are normally distributed. And again, that the mu, the expectation is 10, and the standard deviation about that expectation is 20. So calculate the probability that some return that we realize will be negative. How likely are we to have a negative return, or a return less than 0. And so here's positive 10. A return of 0 is going to be right here. It's going to be half a standard deviation to the left, because remember, standard deviation is 20%. So 10%, which is the mean. To get to 0, I have to subtract, well, half of a standard deviation. So the question is, what is the likelihood of a return that's going to be in this part of the curve? And the first thing we'll do is we will calculate the number of standard deviations from mu, that is this target number, which in a minute we'll call x, as 0%. And so here's my equation. Z is the number of standard deviations. X is the target, what I'm trying to figure out, probability of return less than 0. Mu is the mean. Sigma is the standard deviation. And so I want to know if I go from 0 to 10, that's minus 10%, divided by 20. And so that's scaling this. And essentially I'm going to go 1/2 of one standard deviation to the left. So 0% is half a standard deviation from 10%. So how much of the area under the curve is to the left of 0%? And what I want to do is I want to integrate from negative infinity to 0. I'm going to integrate this curve. I'm going to take the area under the curve, and this is it. And if I do this whole integral, plug all this crap in, do the actual integral, which I'm not going to do, I get 0.3085. And the way I interpret that number is that there is 30.85% of this curve is in the shaded area, and therefore 70%, 69% is in the unshaded area. And so what I can say is that the probability of a return that is less than 0, the probability of observing a return in this shaded portion is 30%, and the probability of earning a return in the unshaded portion is 69%. So for any given mean and standard deviation, if we assume a normal distribution, we can easily calculate a probability range. And we'll do this in Excel using the norm.dist function, which has as inputs the x, our target, the mean, the standard deviation, and this cumulative value. Or we can use the norm est-dist, and the difference between norm dist and norm est-dist is that here you have to have calculated the z. Remember that the z value is equal to x minus mu over sigma. Well, in this one, I enter x and mu and sigma, and it calculates z for me. This one, I had to have pre-calculated z at negative 0.25, and I get the same number. The next example that we'll look at is a range. What is the probability of a return in between 15% and 25%? And what we'll do is we'll actually take two different values and subtract the difference. So here I'm going to calculate the probability of a return that is going to be less than 25%, and the probability of a return that is less than 15%. So the probability of a return less than 25 is 77.34. The probability of a return that's less than 15 is 60, and so then the intersection is going to be this probability minus that probability, and I get a 17% chance of a return that is in between 15 and 25. There isn't a real practical reason to do this. This is just an exercise to make sure we understand what these calculations are. And we'll spend a little bit of time in Excel just practicing these and looking at some of these computations.